In this second video for Chapter 10, we're going to be moving to the independent measures t-test and discussing the new formulas that are involved. So previously for the one sample t-test, our null hypothesis was that our mean of our treated sample, so our single one sample that we had, was going to be equal to the mean of the population. Well, now we have two samples. So we're going to have two unknown sample means that we're comparing. So we have the sample mean or the population mean from sample 1, and we have population mean for sample 2. These are our unknown sample means or population means we're comparing. Now, we could say we want them to be equal, but in order to make it look like we're going to see in the formula and to help us understand the formula, we want to say that the difference between these two is going to be 0. And the way that the difference between these two would be 0 would be if they were actually the same. So I put that here just hopefully to help you understand the formula when we get to that independent measures t-test formula, and hopefully you're going to need to keep those separate come the exam because you're going to see problems for the one sample t-test and you're going to see problems for the independent measures t-test on the exam. You need to know when to use which formula. So the null hypothesis, again, like we said on the previous slide, for the independent measures t-test says there is no difference between the population means. So as I showed you on the last slide, the way we would write that would be H sub O, our alternative hypothesis, the mean of population 1, subtract the mean of population 2, and you get 0 because they're equal to each other. Now for the alternative hypothesis, the idea is that this difference will not equal 0 because there'll be a difference between the population mean. So the alternative hypothesis says there is a mean difference in the population means, so that when we treat sample 1 and sample 2, they come up with different sample means that will then generalize to those population means. So here, alternative hypothesis, H sub 1, is that when we subtract the mean of population 2 from population 1, we don't get 0 because they're not equal to each other. So now we're going to compare the basic structure of the t-statistic. So for our one sample t-test, we said that our sample mean, we took our sample mean and we subtracted that population mean. So we had one sample and we were comparing it to the population mean. We're seeing what was the measured difference, the actual difference that we measured between the sample and the population. And we compared that to our expected standard error, our expected difference, which is our estimated standard error. So now that we have two samples, we have to compare, again, thinking about that hypothesis, we're looking at the difference in those sample means and comparing them to the difference in the population means. So we take the sample mean difference and we compare it to the population mean difference. So again, this is our measured difference from the mean, and this is what we expected to happen, and we use our estimated standard error again. So again, this formula, this is from the previous chapter for our one sample t-statistic. And this is what our formula is going to look like for the independent measures t-statistic. Now, because of what we hypothesize, this is going to be 0. So really what we're comparing is the mean of sample 1 and subtracting the mean of sample 2. And then our standard error formula is going to be a little bit different as well. Again, our hypothesis here was that the mean of the treated group equaled the population mean. And now we say the mean of population 1 subtract the mean of population 2 equals 0. So there's no difference in those population mean. And that's where that 0 here comes from. So overall, the T formula is the mean sample difference and the estimated standard error. That D is just a little bit out of whack there. It's supposed to be on the end of here, estimated standard error. So, as mentioned, the estimated standard error formula is going to be a little bit different. Think about it. Remember that it's how much difference it is reasonable to expect between the two sample means if the null hypothesis is true. because each sample mean approximates the population mean, but of course there's error. So we need to take into account both of these errors, the error in sample 1 and the error in sample 2. So estimated standard error for independent measures t-test is a measure of standard or the average distance between the sample statistic, which is our mean, and the population parameter. So this is what our formula is going to look like. The notation would be S sub M1 minus M2, and this is our formula, the square root of our variance for sample 1 over the n for sample 1 plus the variance for sample 2 over the n for sample 2. Now this standard error on a bar graph is just going to be, you're going to have your bar graph representing your sample means, and then you just see a little line that shows you how big that error is. And I tell you this because, one, it's important to know, but also for this little meme here, where as you see, these are the standard error bars. And this little guy is saying, sorry, I just can't trust you. So why do we add the sample measurement errors, the square deviations from the mean, but subtract the sample means to calculate the difference score? So the scores in the two populations, they're going to vary from 50 to 70 here, this population, and 20 to 30 here. So here's a 10-point spread. So that's the variance in this one, but this population has a bigger variance. It has a 20-point spread. So if you select one score from these two populations, the closest two values are 50 and 30. That's a 20-point difference. But the ones that are farther apart, you see a 50-point difference. So if we look here, there's a 10-point difference in population 1. And there's a 20-point difference in population 2. That gives us a 30-point difference if we add that up. If we look at the differences here, the biggest difference is 50 points, and the smallest difference is 20 points. If we subtract these, so we added those up here, we get, again, a 30-point difference. So that is why we add the variability together. We had the variability was 10 points here and 20 points here. Of course, the formula is a little bit more complicated, but that's the reason that we add together the variance, but we subtract the sample means. So the formula I showed you earlier is only used if n1 equals n2. So that previous formula a couple slides ago, only if n1 equals n2, the sample sizes are the same. Otherwise, we have to use what's called pooled variance, which provides an unbiased basis for calculating the standard error. So this is what that notation is going to look like. Here's variance, and now we just have this little p to denote that it's a pooled variance. Now remember, several chapters ago, we had a mean pooled difference, right? So if we had to take the sample means for two different samples and we wanted to combine them and the sample sizes weren't the same, we did something very similar. So this formula is just the sum of square deviations for sample 1 plus the sum of square deviations for sample 2, and we know how to calculate SS by getting our sum of x and then our sum of x squared. And then again, remember with variance, we take into account degrees of freedom. So this is where we use that degrees of freedom because our sample variance differs a little bit from our population variance. So our estimated standard error then is calculated using the pooled variance estimate. So we take the pooled variance estimate, and this would be like for sample 1, over the n of sample 1, pooled variance, and then again just accounting for it with the pooled variance for sample 2 over the sample size for sample 2, and of course we take the square root of that, and that's going to give us r. So the formula is very similar, it's just we have to use that pooled variance now. We also have to take into account a little bit difference for the degrees of freedom. So we have to take the degrees of freedom for the first sample plus the degrees of freedom for the second sample for this independent measures t-test. So our degrees of freedom is represented as degrees of freedom for sample 1 plus degrees of freedom for sample 2, or the sample size minus 1 for sample 1 and the sample size minus 1 for sample 2. And note, this is the same term as the denominator in the pooled variance. Okay, so for the pooled variance, this is the degrees of freedom that you use. So let's see if we're understanding this. If the n for sample 1 was 10 and for sample 2 was 5, what's the degrees of freedom for the t statistic? So to do degrees of freedom, we're going to take sample 1 minus 1 plus sample 2n minus 1, and that's going to give us 9 plus 4, which is going to be 13.